places. So Nayesh, you've heard some version of this talk before, but actually now I'm allowed to show you all the DESI results that I couldn't show back when I last gave it because the paper is now out of collaboration review and on archive. And I have had the pleasure of having both Subir and Tarun. Actually, I've gotten to meet them at UF in the past year or two, and I really hope we can have you both back to UF sometime soon. And then finally, I was really pleased that I think one person in the audience is Lyman Page, who I actually many years ago had the pleasure of learning statistical mechanics from as an undergraduate in college. And so unfortunately, there will be no statistical mechanics in the talk today, but that's probably a good thing because I wouldn't want to present to the master on statistical mechanics. So today I'm going to tell you about the 4-point function in parity violation. And I like to start this slide, this talk out with a balance, because I want you to keep in mind this idea of balance. What we're really interested in tracking when we use the 4-point function to study parity violation is actually an imbalance between tetrahedrons of opposite-handedness. So if that all sounds a little bit puzzling, don't worry, it'll become clear, hopefully crystal clear, like this crystal balance as the talk moves forward. But I want you to keep in mind this idea of an imbalance of tetrahedron, their mirror image. So this work is done in collaboration with a couple of people I should mention, most particularly Alex Królewski and Simon May, who were both at Perimeter and Waterloo at the time this was done. And Simon's now a postdoc at the University of Bielefeld in Germany, and Alex is still at Waterloo, and he's on the job market, and you should hire him if you're looking for a great cosmologist. And then some of the earlier work I'll talk about was done with me by Bob Kahn and Jamin Hu. Jamin was a postdoc in my group for a number of years, and Bob was a more senior collaborator, and some of their work I'll be touching on as well. And then finally, a lot of this has been contributed to by my own team at UF, listed across the middle of the slide: Alessandro Greco, Farshad Kamal and Ahad, William Mortola Leonard, and Jess Chilino. And Farshad and Alessandro are postdocs with me, and the others are my grad students. So this is really work that many hands have touched, but I think you'll see it's a pretty meaty, complicated topic, so it was helpful to have many different inputs. So the outline of the talk is very simple. First, I'll tell you how in principle we can look for parity violation with the 4-point function. Then I'll tell you how in practice. Then I'll show you some results from BOSS, Baryon Oscillation Spectroscopic Survey. And then we'll wrap up with these DESI results that I had to tantalizingly only show hints of when I last gave this talk to Nayesh. But as I said, they're now public and you can find them on archive. So how can we search for P violation in the early universe? So first of all, I should say what P is. I think everyone knows, but parity is a symmetry of basically taking x, y, and z to negative x, negative y, and negative z, and it's equivalent to a mirroring plus a rotation. And in this talk, we're going to forget about the rotation because we're averaging over rotations because we're assuming isotropy, in cosmology. So just think of parity as a mirror transformation. And the question becomes, how can we search for parity violation that might have occurred at the universe's earliest moments during inflation? We know that if there's real parity violation in large-scale structure, it would have had to come from inflation because we understand the energy scales after inflation sufficiently well. We understand the standard model, and there's just not enough parity violation in the standard model to really be producing large-scale structure parity violation after inflation. Inflation is where it would have to take place because the energy scales of inflation, may go beyond standard model physics. So the question is, how can we use large-scale structure as a laboratory to test this fundamental symmetric nature? And I'm giving you a hint at my answer with the background image. Those with sharp eyes or those who have heard my talk before will recognize this is the BOSS CMASS sample of galaxies. So this is a galaxy redshift survey. You're seeing the RA and DEC, and closer to us, redder ones are farther away. And from this, we actually get the 3D information about the galaxies. And so in this talk, I'll show you how we use 3D maps of galaxies to study parity. Okay, But let's make it even simpler. Let's start with us. This is a chalk drawing, a red chalk drawing by Michelangelo, and it's actually a study that he made preparing to do the Sistine Chapel. And this is the famous hand of God breathing life into Adam. And I thought it's appropriate because parity violation may play a role in the CP violation. We know we need to do baryogenesis, which is why there's something rather than nothing, and ultimately why there's us, why there's humans. Otherwise, if you don't have baryogenesis, you don't have an excess of baryons over antibaryons. So I was quite amused to read recently in the newspaper that they've now found not only this underpainting drawing of the hand, they've actually found Michelangelo's sketch of a foot that was used in the Sistine Chapel. So I think this will inform my next research direction. I'll move from what we can do with our hands to what we can do with our feet. But I haven't yet today. The organizing metaphor will be hands and handedness. So I want to ask you a very simple question. How can you tell the difference between your right hand and your left hand? Well, let's first imagine tracing your hand on a sheet of paper. And I actually got this still from a YouTube video with instructions on how to trace your hand. So if anyone is having difficulty with that, you can find it on YouTube. But I think this audience, we probably all know how to trace our hand. So imagine tracing your hand, and you get something that looks like the image on the right of your right hand if you traced your hand and colored it in, and you get something on the left that looks like your left hand if you traced it and colored it in. So these look distinct, but I want you to now imagine taking a scissors and cutting them out. Well, if you cut them out, you could actually take the image, the tracing of the right hand, and rotate it out of the page and overlap it with the tracing of your left hand. So this is showing you the idea that a 2D tracing can be rotated into its mirror image. So as I said, we're going to be averaging over rotations under the cosmological assumption of isotropy. And so if a parity difference disappears under rotation, it's not good. We can't use it to probe parity. So 2D is not good enough for parity. Even though you started with the right and the left hand, some information is lost when you project them into 2D and trace them, and you can't distinguish them under rotations. However, we can actually tell our right hand from our left hand, at least most of us can. My mother always said that. I seem to have trouble with that. I was a little clumsy as a kid. But most of us can tell our right hand from our left hand. And how do we do that? Well, it's because our hand actually is a 3D object. So not only do we have the shape information that was in the tracing, but we also have the palm, and we have the back of the hand, and we have the thumb. So with this 3D information about the hand, we can distinguish left from right hand. I like to make a kind of macabre analogy here. If you imagine that you cut off my right hand and left hand and put them in a bag and shook them, which would correspond to averaging over rotations, you're randomizing the orientation, you could still pull them out of the bag. And I hope you do this quickly because I want them reattached. But you could still pull my hands out of the bag and reattach the correct right hand to my right arm and the correct left hand to my left arm, because even after randomizing the orientation in space, it's clear which is a right hand and which is a left hand. So this is actually illustrating a kind of profound point, which is that 3D objects have a handedness, or they can have a handedness. So we can use this idea for parity search in galaxy clustering. We need a three-dimensional statistic. So the two-point correlation function is the kind of workhorse tool in cosmology, and it measures excess correlations of pairs of objects over random. And I want you to imagine a line with a given length with two galaxies at either end of it. That's the geometry of the two-point function. And as we all know, a line is 1D. So we immediately know by our discussion about hands that a line, the two-point function, is not going to be good enough for parity violation. Similarly, the three-point correlation function, which measures excess correlations among triplets of galaxies over random, well, that describes triangles. Now, a triangle is also a plane. All the points of a triangle are coplanar. So again, a triangle is two-dimensional, not three-dimensional, so it's not going to work. However, the four-point correlation function is the lowest order three-dimensional statistic, and it describes an excess of tetrahedra over a spatially random distribution. And because it's fundamentally 3D, you have a distinctiveness of mirror images from their mirror partners. You can't rotate one into the other. And this is very easy to demonstrate with your hands. I want you to hold up your right hand, and you can actually do this during the talk. I won't be offended. Hold up your right hand. Imagine putting one galaxy at each of your 3 fingertips and one galaxy at the knuckle of your middle finger. And then do the same with your left hand. And this is actually showing 2 mirror image tetrahedra that you're showing with your 2 hands. And you're not going to be able to rotate the right-hand tetrahedron into the left-hand tetrahedron. They're distinct, even under rotations. So this is important because, as I said, we generally assume isotropy and homogeneity in cosmology, and so we want rotation and translation invariance. And you can see that this construction is rotation and in translation invariant because you can take your hand with this tetrahedron on it and rotate it all around, and you haven't changed the shape. And you can move your hand back and forth, translate it, and you haven't changed the shape. So this idea of using the 4-point correlation function to probe parity was presented for the first time in a PRL by Bob Kahn, myself, and Jiamin Hu in 2021, which actually took till 2022 to get published. So you can find that at the lower right. But if we want to use the 4-point function, we need the right mathematics to describe tetrahedra because, as I said, the 4-point captures excess clustering of tetrahedra above random. And this is where it gets a little bit dense. The math of this turns out not to be simple at all. It turns out that you need something called the isotropic basis. Now, this is a basis of rotation invariant functions. That's a generalization to more than 2 arguments of Legendre polynomials. And so what you do is you take the 4-point correlation function and you write it as a sum of radial coefficients, which I've boxed in a red box, times angular basis functions, which I've underlined with the gold underline. And once you've expanded into this basis, which we call the isotropic basis of these angular functions, all of your physics information is in the red box. All of your information about the cosmological signal is in these coefficients, which we call radial coefficients. So what are these magic basis functions that let us do this? Well, I've shown them here in an equation at the bottom of the slide. They're basically triple products of spherical harmonics. And what they're really doing is contracting to 0 angular momentum. And so this is enforced by the Wigner 3J symbol out there in front of it. This basically says that L1, L2, and L3 add up to 0 total angular momentum. Now, that sounds like technical mumbo jumbo, but it actually makes sense if you think about it. If we had a set of spherical harmonics that was adding up to non-zero angular momentum, that angular momentum vector would define a preferred direction, and therefore it wouldn't be rotation invariant. So the only set of 3 spherical harmonics of different arguments, R1 hat, R2 hat, and R3 hat, that's going to be rotation invariant, has to have net 0 angular momentum, which is enforced by this 3J symbol. So what are these R1 hat, R2 hat, and R3 hat? Well, at the upper right of the slide, I'm showing you a diagram of a tetrahedron. We sit at one galaxy shown by a red point, and we look along 3 sides, R1, R2, and R3, and then the unit vectors of those sides are the arguments of the spherical harmonics. So you're basically breaking the symmetry of the tetrahedron, and you're choosing one special point, you're sitting on that, and then you're expanding the angular dependence around that point in these angular basis functions. Now, for the CMB people in the audience, there's a real analog to this with the basis that's traditionally used for the CMB bispectrum measurements, because in that case, the red point is us, the observer, and the 3 other points are all on the same spherical shell. They're on the CMB sky. So here, we're letting one point be a galaxy instead of the observer, and the 3 other points can be on different radial shells. They can be at different distances from the primary point. So if you're interested in more of the mathematical properties of these functions, Bob, pictured lower left, and I wrote a really long paper about all of their functions, all of their properties. And I also was able to find a generating function, much like the Legendre polynomials have a generating function. I was able to find a kind of function where you expand it in a series and it generates these basis functions. But all of that's not so important today. For today, what's important is just, understanding that we're seeking these red boxed radial coefficients. Those are going to tell us about the 4-point correlation function measurements. And so an interesting property of this basis is that it actually splits into even and odd parity modes. Now, you'll all remember that the parity of a spherical harmonic goes as L. So you can see that the parity of the set of three of them would go as L1 plus L2 plus L3. Therefore, if that sums an odd number, it's going to be an odd parity basis function. If that sums an even number, it's going to be an even parity basis function. So the odd modes actually capture an imbalance of tetrahedra in their mirror images. So this is why I started the talk with the scale. We're actually measuring an imbalance between tetrahedra and their mirror images. And here I'm showing you a tetrahedron and its mirror image. And we do have to have an ordering of the sides for technical reasons. So R1 is distinct from R2 and R3, and they're ordered as R1 is less than R2 and less than R3. But you can imagine I sit on R1 and I go in the direction of the larger side and then the largest side. On the left-hand tetrahedron, I'm going clockwise as I do that. But in its mirror image, as I go from shortest to longest side, I'm going counterclockwise. So you can actually imagine a mirror transformation of these tetrahedra as basically inverting the order that you'd go around from shortest to longest side as you sit on the red primary. It's taking it from clockwise to counterclockwise. What's interesting also is if you imagine taking this left tetrahedron and pulling the R1 side through the plane formed by R2 and R3, you would get the right-hand tetrahedron. So if you actually turn the tetrahedron inside out, you would get its mirror image. Now this makes sense because the odd modes all turn out to be proportional to the signed volume of the tetrahedron, which is called the scalar triple product. And so if you inside out something, it makes sense that you would pick up a negative sign on the volume. The volume is going to flip sign because what's inside is now outside. So mirroring actually is equivalent to inversion of the volume, and it therefore makes sense that the signed volume is playing an important role in all of these odd parity modes. So I should note this is where things diverge a bit from the CMB bispectrum literature. There is a wonderful paper, I believe, by Tarun and Mark Kamiankowski noting that one can measure the CMB odd parity bispectrum, but generally people have focused on the even parity CMB bispectrum. Okay, so I've now told you a little bit about the basis we're going to be working in. I now need to show you an algorithm. How do we actually, in practice, measure the radial coefficients? Well, we can simply use orthogonality of these basis functions, which I'm duplicating here again, to project the densities onto the basis by integrating against it. Now, I want you to notice this basis factorizes. It splits into something depending on one unit vector, R1 hat, another R2 hat, and a third R3 hat. It splits up. And this factorization is extremely powerful because what you can do is you bin the galaxies into spherical shells. You do the angular integral against the harmonic on each shell, and then you only look at combinations of 3 shells around the primary rather than looking at combinations of sets of 3 galaxies around the primary. So then your scaling is number of shells cubed rather than number of galaxies cubed. Number of shells is order 10, so 10 cubed. Number of galaxies is order 10,000 around a primary, so 10,000 cubed, so a lot worse. So here at the bottom of the slide, I've made a cartoon just kind of showing how this looks, showing basically you're binning into shells around one object, and then showing that you have to do that around every object. So this results in a very fast algorithm to do this, and it's actually kind of analogous to the CMB bispectrum algorithm that one uses. So finally, one point about the computation, it turns out that this algorithm is a very high arithmetic intensity, so it does a lot of flops, floating point operations per second. And so that problem performs really well on a GPU. So we created this GPU-based code called Cadenza, which is a code for 2 through 6-point correlation functions that gives us 140x speed up over the same algorithm on the CPU. And this is a cadenza, which is a soloistic fast section of a piano concerto. This is a cadenza to Mozart's Piano Concerto number 20, written by Beethoven. So, cadenzas have a lot of notes. We have a lot of galaxies. So I thought it was appropriate. And for those who don't really care about flops or GPUs, the bottom line is that this algorithm on the GPU lets us do the 4-point function for 1 million galaxies plus 32 times the number of randoms in about a half an hour on one GPU core, and a similar amount of time for DESI Year 1 data. So this is work done by Craig Warner with me and a few others at UF, and Craig gets a cameo shot on the left here. Okay. So I've told you about our basis, I've told you about our algorithm. One more piece needs to be introduced before I can show you the data. How do we assess significance? Well, like any good science experiment, you need error bars. So our error bars are covariance matrix. Covariance just tells you the correlated error bars of the measurement. And the gold standard in cosmology has been to use mock catalogs to do this, fake data sets realized on the computer. But unfortunately, our data vector has 18,000 degrees of freedom, whereas the number of mock catalogs we have for surveys like BOSS and DESI is only 1 or 2,000. And you can't form an invertible matrix from such a small number of mocks relative to the number of degrees of freedom. So we instead use an analytical template based on a Gaussian random field. And here I'm showing you, in the lower half of this matrix, I'm showing you the noisy and non-invertible covariance estimated from patchy mocks. That's just the name of the mocks for BOSS. And on the upper triangle, I'm showing you the analytical template that's from our Gaussian random field calculation, and they're indistinguishable by eye. So the Gaussian random field actually gives you a pretty good model for the covariance. And the advantage is, since it's calculated from theory, it's not noisy and it's perfectly invertible. So this was a major push led by my postdoc, who's now a faculty in Germany, Jamin, who's pictured here. Here I'm just going to flash this slide. Those who are really aficionados will recognize 9J symbols. There's a lot of angular momentum math that goes into computing this covariance in the isotropic basis, and some of my grad students shown at the bottom have dug into that a bit more. But with all these pieces in place, I can now show you what I think everyone's probably been waiting for, which is the actual data. So we can look at the BOSS data and the DESI data, and that'll bring us to the end. So first of all, how does the measured 4-point function look in our basis? Well, here I'm showing you a split by the L modes. So 1, 1, 1 refers to the L's of the spherical harmonics. Notice it adds up to an odd number. It adds up to 3. And here I'm showing you only parity odd panels. So 1, 2, 2 is 5, 1, 4, 4 is 9, etc. And I'm showing you the CMAS sample from the BOSS survey in the North Galactic Cap and in the South Galactic Cap in red and blue. And what we've done is we've mapped the dependence on the 3 sides of the tetrahedron to a single radial bin index to make it something you can visualize. So just imagine reading a matrix through in row major order. We've mapped the dependence on 3 tetrahedron sides in each coefficient to just a single index. And so this is kind of a trick question showing you these plots. What the data looks like in our basis is it looks like noise. It basically just looks like random fluctuations above and below 0. And so where the power of this really comes in is taking many, many of these panels. We have 23 panels like this, and co-adding them up. And when you co-add them weighted by inverse covariance, then ta-da, a signal may emerge. So this is the result we got a few years ago with the BOSS data, and it's very simple. On the y-axis is probability, on the x-axis is total parity violating signal measured by chi-squared with respect to a 0 model, no parity violation. And the black histogram is just mock catalogs, fake data for the survey that has absolutely no parity violation. And so what we can do is we can fit a Gaussian to that distribution of mocks, measure the width of that Gaussian, and then ask how far away is the data in units of that width from the mocks. And so the data is this orange line, and it appears that there's a 7 sigma tension between the data and the mocks. The data seems to have a quite high preference for non-zero parity violation. where we use the MOCs with no parity violation as our null hypothesis. So that was the status 2 or 3 years ago when we had this paper out with my postdoc John Min at that time leading it. But we have much, much better data now. We have DESI year 1 data. So I will spend the last couple of minutes showing you what we found in that data set. So DESI is an exquisite instrument. It's highlighted here. It's up on a, pedestal. They thought in the 70s that would help with the wind. It actually hurts with the wind, but it does make it look nice in pictures. And DESI is at Kitt Peak National Observatory just outside of Tucson. And it's a really incredible instrument. It has 5,000 fiber positioner robots that are actually able to reconfigure the entire plate in 1 minute. And so it can get as many as 150,000 galaxy spectra every night. And I've actually observed for DESI, and we've 150,000 in one night. So it is, by some measure, 90 times more efficient than BOSS. BOSS took about 15 years to get 1 million galaxies. DESI will take 5 years to get 30 times as many galaxies. So DESI year 1 is already done, has been on disk for a few years now, and that's what I'm going to tell you about the results from. So I'll just cut right to the chase. This is basically the same type of plot I showed you for BOSS, but it's showing you the DESI data results. Now, you might scratch your head and ask, why are there 3 histograms here instead of 1? Because I told you we'd make a nice histogram of the MOCs with no parity violation and we'd compare the data. Well, the answer is simple. We have 3 different kinds of MOC catalogs for DESI. So I'll briefly step you through them. Abacus FFA in yellow is an n-body simulation set, but the FFA is an approximate fiber assignment scheme that is tuned to emulate the true fibrane of galaxies on the sky, but we don't think it's as accurate. Then Abacus Alt-MTL stands for Alternative Merge Target Ledger, and it's a very, very high fidelity way of converting the MOC catalog to have the DESI fiber assignment on it. And then finally, EasyMOC FFA is not a high fidelity MOC, it's not n-body, and it doesn't have the right fiber assign method. So it's kind of just here for comparison to show you that these subtleties of how you do your simulation and how you assign fibers to the simulation can affect things quite a bit. But what I want you to concentrate on is the red histogram, because that's our most faithful n-body simulations with the most faithful fiber assignment method that mirrors DESI most closely. And basically what hopefully stands out is that the blue dashed line representing DESI data is quite a bit away from the distribution of the MOCs. And the image of all of you is actually covering on my screen the sigma, but I think it's about 11 sigma away. Let me see if I probably won't be able to move it, but the legend at upper right, DESI S sigma, is telling you how many sigma away the blue line is in units of the width of the red distribution. So this is for the North Galactic Cap. Then we can do the same thing for the South. And again, we also find a pretty robust tension between the data and the MOCs. So one thing we can do to address this tension is kind of take a trick from the book of the CMB people and take patches that are spatially separated on the sky and therefore should have uncorrelated noise. Now, if there's a real signal from inflation, we think it should be the same everywhere by isotropy, so it should survive cross-correlation. And this is a standard method in the CMB, apparently. So we split the north into patches. Here in blue is one patch, and then the kind of shades of pink and lavender are 3 other patches, and we don't use the scarlet region that connects them. So we have 4 spatially separated uncorrelated patches in the north, and we can cross-correlate our signal and see if it survives that cross-correlation. And unfortunately, it doesn't. Here, I'm showing you cross-correlations performed on the EasyMOC MOC catalogs in cyan, and then on the DESI data in the blue vertical line. Now, you might wonder, why did we not use our better MOCs, our Abacus MOCs, for the cross-correlation? They actually were made with replication, so they are not spatially uncorrelated with themselves, so you would see a spurious signal from them, so they can't be used for this cross-correlation, but the EasyMOCs don't have that issue. So the bottom line is, this cross-correlation method does not detect any inconsistency between the data and the mocks. It's saying that in the cross, the DESI parity violating signal sort of seems to go away. We can also do this in the south. Here are the 3 patches we use for the south in RA and DEC. And again, we see very consistent with the north that the cross correlation doesn't pick up any parity violation in DESI. So that is the observational status right now. The way I wrote the paper with my colleagues was basically just to report the numbers we got and say, this is attention, we'd like to understand it better. We need to better understand the difference between the autocorrelation and cross-correlation techniques, and we need to perhaps wait for more data. So I want to close on an optimistic note. This is a forecast for what DESI year 5 will do if we see a 5 sigma signal, which we did in the BOSS data set. So here I want you to focus on the red points and follow up the red vertical dashed line. That's showing you the number density that DESI year 5 will have, and it's showing you that DESI year 5 should be able to detect parity violation at about 30 sigma if it's real in BOSS. So DESI year 5 is almost on disk right now. The survey is ahead of schedule, and it should finish pretty shortly. So the point is, when we get the 30 million galaxies of DESI year 5, we're going to have the statistical power to knock this one out of the park and just get a tens of sigma measurement if it's real. And so that should shed pretty definitive light on this weird issue between the cross and the auto that we have. So I think I am pretty much out of time, so let me just give you the summary slide. I've shown you that the galaxy 4-point correlation function is sensitive to parity violation. I've shown you a basis for it. I've shown you a fast algorithm to compute it that exploits the GPU. And I've shown you how we measured this on 1 million galaxies of Sloan Digital Sky Survey BOSS, and also 1 million or more galaxies. There's actually about 2 million of the DESI year 1 luminous red galaxies. And I've shown you we see statistically significant evidence in one measure, which we call the autocorrelation, but we don't see it when cross-correlating sky patches. So I think the summary is really, we live in exciting times. This is a tension that's there in the data right now, but that in the next few years, DESI should have the statistical power to either definitively detect or rule out. So thank you very much for your attention.
Thanks very much, Zach. That was very interesting. I bet we have some questions. I saw him first, so.
Hi, Zach.
Hi.
Can you hear me?
Yeah.
Okay. So I wanted to ask you about the auto measurements. So, you know, some of you guys showed that the auto can be sort of mimicked by the mismatch in the 8-point function between the calibration simulations and the data. So are you doing anything on the abacus modeling side that will sort of get rid of this mismatch so you can trust the auto signals better?
Yeah, that's an excellent question, Arca, right? I think I recognize you, but it's very small on the screen. Yeah, that's an excellent question. And what you said is completely correct. A detection in the auto could be mimicked by if there's a mismatch in the 8-point function of the mocks, because the 8-point function is the covariance of the 4-point function. So basically, if you've misestimated the covariance, you could get it wrong. Unfortunately, we don't have an algorithm to measure the 8-point function. We do have algorithms to measure the 3, 4, 5, and 6-point functions. We have not measured the 5 and 6-point function. We have actually pretty exhaustively measured the 3 and 4-point function of the simulations and of the data, and we've done consistency tests between them, and it all looks pretty consistent. So we know that the mock data mirrors the real data up to the level of the 3-point and even parity gravitationally induced 4-point function. We don't know anything beyond that. And I think, yeah, this question of how well the data and mocks, how good of a model for the noise is the mocks. This is, I think, one of the cruxes.
Thanks. And Yash?
Thanks, Zach. So, okay. So I want to understand this statement you make that in the cross you don't see any significant effect, but in the auto you do. So does it mean that in some patches you have more left-handed tetrahedra than right-handed, but in other patch you have the opposite, they have more right-handed than left-handed, so when you cross them, the thing cancel? Is that what it means?
Yeah, I'd have to think about it more carefully, but I think that is probably what's happening, that it's basically, it's not coherent across the patches as you would want it to be if it were a real signal, or at least, I think the other question is the cross correlation as sensitive as the auto? Because you could have a measure that's more robust to false positives, but also more likely to produce a false negative just by dint of less sensitivity. So I think your interpretation could be what's going on if if there's no real signal. But I think we still have to understand, is the sensitivity there in the cross at the same level, to a signal as the auto.
Thanks.
Glenn?
So, hi, Glenn Starkman. So, how do you know that the signal, if it's anisotropic, is not real? I mean, you're making an assumption about the model, but we see statistical isotropy violation evidence for that in the CMB, and parity violation is very closely tied up with isotropy. So maybe they go hand in hand here.
Yeah, excellent question, Glenn. And I think this is the right conference to bring out this idea that, if the inflationary signal is anisotropic, then all bets are off, because then you wouldn't expect the cross correlations to actually pick each other up, because you could have real parity violation, but different shapes of it in different parts of the sky. And I think, there are inflationary models that do actually have anisotropy as well as parity violation. So yes, that would be one explanation for what we're seeing. If you have an anisotropic but real signal, that would explain why we're seeing something in the auto but not the cross.
If I may add on to that question, do you see the signal go away in the cross correlations among the pink-ish patches, and not between the pink and blue? Or, do you show the result that contains all of the cross correlations between all of the pink and the blue, or can you do this analysis separately so as to check different scales on the sky?
Yeah, so what I showed you is all of the cross patch pairs. So there are, I think, 7 patches, 4 in the north and then 3 in the south. And so there's something like 7 times 6, which is 42 divided by 2 for, symmetry. So there are 21 pairs of cross patches that one can do. And these histograms I'm showing kind of capture all of them. But I think it would be super interesting to pursue your suggestion and basically look one at a time, with, single pairs of patches. What do we see? Because that could tell us if, that would give us a more granular sense of what's going on.
Thank you. Sabir.
Zach, you said this could be primordial in the sense of generated by inflation. Could you suggest what sort of tests one could perform with the CMB that might be a useful cross-check?
Yeah, excellent question. So it turns out that because the CMB is basically a 2D spherical surface, it's not sensitive to parity violation on the scales that we're seeing it here, which is a couple hundred megaparsecs. And I actually just put a paper on arXiv where I was able to compute in the Sachs-Wolf limit the CMB response to a matter field that violates parity, and basically show it's suppressed by the scale of the tetrahedron divided by the distance to last scatter. So if your scale of tetrahedron is a few hundred megaparsecs and your distance to last scatter is 15,000 megaparsecs, then it's a quite heavy suppression. So unfortunately, I think the CMB is kind of blind to the scales of parity violation that we may be seeing here. On the other hand, if you have very, very large scale parity violation, where you have tetrahedra that are the order of 500 megaparsecs on a side, then you're exploring the limit where the CMB is actually curved. And then, it turns out it is sensitive to parity violation. So I guess I would say I think the CMB is a fairly complementary observable, that it gives us an eye, a lens on a different scale of parity violation than the large scale structure.
Thanks. We have time for about 1 minute of a question.
So SNe Ia survey has very complicated angular selection function, as we see right now here, which may potentially have big impact on your measurement. And I don't see the error bar of your measurement. So could you comment on the error bar of your measurement?
Yeah, that's an excellent question. So indeed, this plot kind of shows the gray is the DESI kind of completeness, and that you can see it's in some areas it's very good, and in some areas it's really, we haven't had enough passes. This is folded in to these distribution of the Machs that I showed, because we basically make the angular completeness of the Mach match the DESI angular completeness. But, it is challenging to do that perfectly. And I think one hidden advantage that I didn't mention of going to DESI year 3 and year 5 for this analysis is the survey will become much more complete. The footprint will be less ragged and less, inhomogeneous. And so not only do we have more statistical power, but I think we can trust the DESI year 5 measurement more because the angular footprint will be easier to control.
Okay, thanks very much. So let's thank Zach again. And wish you a good night's rest over there. We're just starting the day here.
Yeah.
Okay.
Thank you so much for organizing the remote session. I appreciate it. Take care, everyone.
Bye-bye. Yeah, and we're still setting up. So next up, if that's going to take maybe just a few seconds more.
I don't know what is next. I don't have my laptop in France. So this is Pogosyan.
Sorry?
Now his talk.
His talk, yes. Okay, so now we have Dmitry Pogosyan telling us about large-scale structure via critical events theory. Once it's set up.
Does it work? Yep. I somehow don't hear it. Thank you, first of all, very much, organizers, for inviting me and for organizing this very exciting conference, I would say. So the focus of this conference was basically on the tensions of the standard model in our epoch when data is overwhelming, very precise. We talk about 1% precision of determining different parameters. And it's maybe last day of a conference, but I want to go back, make a step back, and state that, well, there is some value in actually just trying to have some crude, relatively straightforward understanding from a first principle without any error bars, without any data. And just when we expand our knowledge of how universe works, at the end of the day, there is a trail of a relatively simple story that you can explain to all the people around without reference to the significantly precise details. And so in my talk, I will not have any data, any error bars, anything. I will have numbers 2, 3, and 4, and 5, and 6. Right? Okay, so we are talking about the very basics. So it is a gravitational clustering in a pressureless medium, no baryons, no nothing, just hierarchical clustering from a Gaussian initial conditions, which goes up and provides our halos of different masses at different redshifts, and structure, large-scale structure between those halos, which connects with the overdense bridges, the clusters, and so on. So depending on the timing, on the time, what serves as these halos have different mass and have, in some sense, different physical meaning. At redshift 3, we would be talking about perhaps galaxies as being nodes of the large-scale structure. At redshift 0, we'll be talking about clusters. So basically, we are talking about objects which are just collapsed, and the structure that connects between them, which do not fully collapse and fully virialize. This system is very, very special from the point of view of the equation that governs it. And special aspect of this system is that initial condition is determined by one single scalar field. So yes, you are having moving matters, you have velocities, you have densities. There are 4 fields overall to set up initial condition in general case, but in cosmology it is only 1. You don't have rotational modes, and you have adiabatic initial condition, which links density to velocity potential or gravitational potential, whatever it is. So, which means that in principle, you should be able to learn something just from initial conditions, as a properties of one single scalar field. And yes, in some sense, you almost want to learn something which is model independent and which is qualitatively always holds. So that will take for illustration a density field as our initial scalar type initial field of initial conditions, and what we can do with it. And Dick Bond, many years ago, said, okay, we can look, first of all, at the maximum of those fields. So what is the maximum? Maxima, why they're important, is because when gravitational stability builds up, amplitude of the density and homogeneities grow, and at some moment where they are the most overdense, they start collapsing and forming our halos and collapsing objects. So we could, this field always suffers or has to deal with the fact that you need to smooth your density field with some scale. And in principle, structure is hierarchical, so you should consider smoothing with the different scales. But every picture you see in many talks, it has one particular smoothing when you draw it here. So if you do it that, and you will, where is the pointer? Pointer. Here it is a pointer. Right, and mark, so you can mark your peaks of a density field. You can count them. You can study correlation function. We're talking about initial conditions, but it has a particular scale. So all of those peaks are actually, when you smooth with a particular scale, has the same mass if they form a halo at some moment. So this slice of initial data is not picture of a constant time of the halos, right? So every peak here will form a halo at a different redshift, at a different time. It will form it in a spherical collapse picture when its value reaches a critical density, and from the point of view of time, and that's actually pretty good, more or less. So if you actually want to get a constant time image, you need to be able somehow to smooth different regions with a different scale so that heights of every peak are equal. That is never practically done, and even I'm not doing it. So next, after the peaks, you go down in a density threshold. You'll choose your redshift. You say, I want my halos to be at a particular mass, at a particular redshift to be formed. What's happening with the regions below? And you build a concept of a cosmic web of elementary bridges which connect halos progenitors, and during nonlinear evolution, they will got a little bit more of constant due to nonlinear evolution, be more visible, more overdense. So filaments are, at a given scale, a transient phenomena. They are existing in a kind of final matter distribution only when the scale at which they are defined is mildly nonlinear. If you go further, the scale becomes further and further nonlinear, and filamentary structure basically hierarchically propagates to a larger scale. So there are some remnants at a fixed scale, but then so it goes down. Hierarchy goes further up. So as opposite to the halos, when they're formed, they disconnect from a further universe expansion, and they are fairly stable. They may merge, etc. But filaments are more transient phenomena, and that should be remembered. So now you may want to track those filaments with the geometrical lines, and you take a random field of, for example, initial conditions, and what you define the ridges. And basically, there are peaks, and the ridges are those markers of those filamentary bridges that connect the neighboring peaks. So what is important that every filamentary connector from peak to peak goes through a saddle point, like in the mountains. There are two saddle points here, two peaks, and that is their connections.
The Kulin Mountains.
Huh?
It's called the Kulin Mountains.
Yeah, yeah.
Jurassic period.
Yeah, that's so you can do it in a software. Often used software is dispersed by Thierry Sousbe, who I don't know, left the field after that as astrophysics and moved to Japan. Your picture at the end of the day is the position of the peaks at a given smoothing, and gradient lines which follow the ridges, which connects the peaks through the saddle points. So for me, it will be more of perhaps a tool this time. Yeah.
Quickly ask, so you always discuss peaks and saddle points of the density,
Yeah.
not of the potential?
No, density.
Is there a reason which you will
Yes, there is a reason. So first of all, and the main reason is that our statement with Dick Bond, that over densities that you see in initial field at a mildly nonlinear stage are largely image of what was in initial conditions. So that's why I'm studying density distribution in initial conditions. You could study flows and potential flows, and that would be a little bit different story.
Could you ever get, if you look at some density fields, could you ever get a situation where the saddle point sort of breaks and then it picks up again?
That is critical events theory, which maybe I will reach, but with the speed I'm talking, I may not. Right? Okay, so one thing would,
Can I just say, of course, we looked at the gravitational potential.
Yeah.
Of course, there you don't have an absolute value for the height because it's just fluctuating with the nearly scale invariant spectrum up to, to large.
well,
That's the reason.
I would a little bit say more. I don't like gravitational potential. No, and I mean because it is only gradients of it which matters. And it has a very nasty power spectrum. It's really one single slope with tiny wiggles, and the geometry of that can be done, but not as easily interpretable, I would say. All right, so one thing which you get from that picture is that question with how many neighbors your peak is connected. So how many filamentary bridges connect them to something else. If you do a kind of complete connecting picture, so you actually connect with through every saddle point that you need, it doesn't guarantee you that those lines are actually correspond to dense filaments. They are dense close to the peak, but they may fall off even to negative over density along the way. However, they will still be useful. Still, you can, if you reconstruct the density field, you can be talking about connectivity of such web. And just by counting how many connectors it is. And interesting enough, it is a rather simple theoretical estimate what should be a connectivity in a Gaussian field in 3D. And it is basically twice average number of saddles over number of peaks, which would you take Dick-Bone's result from BBKS is 6.1. So on average, peaks are connected to 6 other peaks with a gradient bridge lines of the filament. So that's the first number of 6. So that's one result. And this is absolutely general result for a Gaussian random field. Three-dimensional, yes. So my images will not correspond to what I'm saying. In a sense, my images are 1D and 2D, but I will be talking about only 3D values. I cannot visualize things in 3D. My mind hurts. So in that sense, all the numbers you see here are much smaller than 6, because that is a 2D picture, and this is a 6D picture. Notice that 6 would be if you have a cubic grid. That's 6. Here is some topological defects. It's not exactly a cubic field. And it is a real number, right? So if you go and measure it in a just Gaussian realization, well, in a simulation, this is in simulation, you start with a linear Gaussian initial condition when it is 6.1, and it drops with a redshift as you evolve if you smooth a field on a fixed scale, because you become more and more non-Gaussian. And in principle, there is a series that describes this drop. It is mildly non-Gaussian field, and non-Gaussian correction can be computed.
And Dmitry, just a clarified question.
Yeah. For a Gaussian field, it's not. It is details of the distribution will. Average number isn't. So, right, and then the timing of those curves are dependent on a cosmology. And because when you deal with a large-scale structure, a lot of things, the timing is dependent how linear perturbations grow by d of z. And that is cosmology dependent. So once you reach a given height, you are probably in more or less the same position of over density. But at what redshift it happens depends on the cosmology. Okay, so this summer, my summer students, three-year undergraduate summer student, pick up to that. And in our original paper, we didn't even use CDM. He did it for lambda CDM. And this is a distribution of connectivity of the peaks, not just an average one. Average is around 6, but the mode of the distribution is at 4. So that is the most probable value of connectors the peak will have. So what my student was tasked with is to have a look what is happening if we now put restrictions on filaments, asking them to be overdense and not to fall below some threshold along the way. So kind of quote-unquote observable ones. And if that is a complete skeleton when there is no restriction on the filaments, and then when you force them to be overdense, not underdense anywhere, you start losing some connectors, of course. And it goes, you lose and lose, and at around 1.25 sigma, filamentary threshold, you basically have a disconnected system with maybe one long percolating connecting cluster. And Tarun, recall our work on percolation, that is somewhere a little bit more than 1 sigma for the 3-dimensional Gaussian fields. And indeed, that is to some extent probably the same result in a different language of connectivity. If you look in more detail, again, my student this summer did it. So this is a graph which shows this, what is the fraction of the halos have what connectivity, depending what constraint on overdensity on the bridges I will put, right? And if there's no constraint, most of them have 3 or more connectors, that's the red line. If there is a lot of overdense constraint, well, there's no filaments like that. It all drops to blue line, which is just unconnected at all. There's no filamentary bridges. Orange and green is one bridge, and green is 2 bridges. And there is this characteristic overdensity at around 1.2 sigma, when basically the hierarchy becomes from in order from no connectors, 1 connectors, 2 and 3. So there is a characteristic overdensity which should be used at the next step to describe a little bit physics of the filament.
Connectivity basically determined by the shape of our spectra?
Practically not. A little bit. In the distribution, you notice lambda CDM. In the distribution, lambda CDM was a little bit different distribution. That's a black line. If you do power law spectra, well, they're more or less on top of that. So this thing with the running slope is a little bit different. So there's a weak sensitivity on a slope, but not awfully great. Okay, so it's actually introduction to my talk, so I have to move. My talk is about not filaments. It's about halo mergers during evolution. That's where critical events come from. So as we progress in time, halos merge, and we could look at it as a progression not in time, but as a progression in slices of overdensity, or smoothing slices, right? So basically, it's a progression in mass, so progression in a size of a smoothing filter. So here is, I cannot explain that. I cannot understand this plot at all, but no, underlying field, which is done here, is smoothed with a sequence of a little bit larger and larger windows with rather small steps. But what is on top is 2 hours of explanation. So let's look at one-dimensional case. So what is happening with a field when you start smoothing it? You have 2 maxima. In 1D, you have a minima in between. If you smooth it a bit more, there is a moment when the minimum merges with one of the peaks nearby, with a lower one. And that is an event of a disappearance of a pair, topological pair of minima and a maxima. That is what we call a critical event. It does not happen at any given R slice anywhere, but in an extra-dimensional space, it is a point event. And after that, you smooth a bit more, and you have one single peak. So this is a picture which actually almost refers to introductory chapter in BBKS when you were talking about some peninsulas there, if you remember, Dick. Yeah. But so we were mostly motivated. He went along with. So this is, yeah, BCA, so that would be better reference. Not better, but additional reference to be put. So you increase the smoothing, it's one-dimensional field. There are tracks of peaks and minima, and at some moment they disappear and merge. So that is what is happening in a, just looking from above on one-dimensional slice. You have a track with a smoothing scale is vertical, position is horizontal, minima, maxima, it disappears. And that actually signifies that the peak which had this track start merging with the peak which is surviving. So if there is nothing in between, that means it goes into that peak, and that is kind of, in our language, a direct merger. So for example, this line will also eventually merge with the surviving halo. It's only a single one, but it first merges with another one, and then the other one will merge with this one. So this critical event does not describe a direct merger of the third peak to the surviving. If you look very carefully, you realize that it is not that this peak merges with this peak physically at the moment when they are smoothing scales are the same, because that would mean that always you have mergers between two equal masses. That is not what is happening. The merger is complete when overdensity at the moment of the disappearance of a satellite is equal to the overdensity in a surviving peak. So those lines where deltas here and deltas here at the different smoothing scales are equal are 2 points of the same time. So if I couldn't draw the line of an equal time because it's only defined on the trajectories. So if you look at a very big picture of that, you see that there is one surviving peak, which I just centered my picture on, and what is in a green are direct mergers into that peak. So this guy, there's nothing in between, so it goes here. This guy goes here. Those critical events in green are not direct mergers. They will come step by step into the surviving peak. So what you want to do, you want to count the number of direct mergers, the peak experience. Vertical line is a smoothing scale, which is is a mass of a peak. So you can ask yourself, I cut mass here, I cut mass here, so while my surviving peak went from one mass to another, how many mergers did it experience? So you notice that all those merger events lie within some cone, and it is a past cone, and it is essentially a cone you would think from which surviving peak accumulates its mass. It's a spherical image in an initial conditions, and as its mass grows, it grows, 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 and grows. If you think a little bit more careful, well, it may not be exactly the mass, it may be a little bit larger cone. So there is what is the width of the cone within which we have to count our critical events. The cone is not straight because the position of the surviving peak varies. As you change the smoothing, it moves around in its initial conditions. But fortunately, that does not matter because the volume of the cone is insensitive to how you shift different layers. So if my job is kind of determine the width of this cone, and if I work with a Gaussian smoothing, I should convert my size of the peak into equivalent top hats. That's one parameter alpha. So it is something proportional to that. But maybe I need to have some correction. And correction will be actually that I need to go to twice the radius, not to a single radius. And if I go to twice the radius, I see that I capture all critical events, which I determined before I drew the cone. And all those critical events tend to lie on an edge of this capture cone.
So after all this merge, you end up with a single, you describe everything else as right?
Yeah, in this sense, in this picture, this is one surviving peak at the largest possible mass, which collected its mass from here to here, from that regions. And as it collected its mass, on that plot, it had 1, 2, 3, 4, 5, maybe that one also should count, 7 direct mergers.
If you count the time at which you have this final output in terms of the linear density,
Yeah, so...
it's still 169?
You still what?
It's still the linear density
Yeah.
value corresponding to this formation.
To some extent, it goes a little bit backwards. If you have that realization, you have overdensity here with this smoothing. And if you say, OK, that's overdensity of 1, So that is not yet a real peak. It doesn't form the halo yet. If it's over density 2, you say, oh no, that's a peak which is halo at redshift a little bit larger than 0. So that when it was 1.68. So you assign timing. But in terms of a mass slices, before that you don't care about it. 5 minutes, okay, that's good. So, how would you count it? Well, it would be good if you knew the density of those critical events in an extended space of position and smoothing scale. And that's just an image of how it looks in 2D. And that is what was done by us in a paper led by Karantan a few years ago, that we developed a series of number density of critical events in the extended space. You could imagine that it involves integration of a distribution of a third derivative of the field and things like that, which is, of course, proportional to the fourth power of a smoothing scale. It's number density in 4-dimensional space, but has this coefficient recognized. It's actually not from number density of 3-dimensional peaks, but there is a kind of extra things here. And gamma is a spectral parameter which actually determined not by the field and its first, second derivative, but by first, second, and third derivative. So it's actually closer to unity. So if you, and total number is from that mass to that mass, how many critical events I had, which was in the same mass interval. So basically what I'm talking about, I go, for example, mass to 10 times the mass, and I count in how many critical events which were at least themselves as a single mass one. So I go decade in masses and count in critical events which are no less in mass itself than the starting my mass, right? So they're relatively major ones. So the tiny one from the bottom are not counting. It's just between two slices of the cone. Well, we'll put the number for a power law. There's an argument that it is twice top hat scale. And what we first of all see, that the number is, factor in front is of order of 1. Depending on a ratio of the starting and final mass, log 10. Beta is our parameter which we 2 multiplied by alpha, which was 3.1 if it is twice top hat radius, and if you change it, it's a little bit changes. N is a slope. There's not that much strong dependence on the slope. If you take n equal like -2, it's a slope of power spectrum. It's for power law spectrum. And if you take n like -2, which is like at the galactic scales, you get, so when mass of the halo increased by a factor of 10 to the 6, so you go from 10 to 9 to 10 to 15 solar masses, for example, at redshift 0, it experiences on average 10 direct merges with masses no less than 10 to the 9. And if you increase a mass of the halo by a factor of 10, then number of merges is 2. And that is a very general result.
These are like major mergers?
So major mergers is defined by the fact that the mass of a merging satellite is no less than your starting mass of your interval. If I go from 10 to 9 to 10 to 10, then I'm counting mergers which carry mass no less than 10 to 9. And if I go from 10 to 9 to 10 to 12, I'm still counting all which is no less than 10 to 9. Because that is basically the cut at the bottom of my cone. Now, in principle, that's where the talk starts, because this is very naive approximation. I took average density, and I multiply by volume of a cone, but I know that my density is not uniform. All my guys are actually clustered on the edges of the cone. So maybe density of the critical events are actually sensitive. Well, the appearance of a critical event is correlated with the fact that it's near the peak, and I need to take into account. And you do that, and you do a correlation function between critical events and peaks. That would be more accurate correction. You measure the correlation function, and that is what our cutoff where it was, 3.1. So you see that most of the critical events are indeed clustered around the edge, and this is already the field, guys, which are not probably related to this peak. You do more accurate thing. I need like 3 minutes to finish the sentences. And you can go and run disperse, and you find connecting bridges, and you know that the peaks which are actually collapsing and merging together, they are the ones which are connected by filament going through a saddle point. In 3D, critical events is the disappearance of a peak with a saddle point of filamentary type. And so 2 peaks which are not connected by a filament line will not merge together, only the one which do. And you can just see which one does and which one do not. And you get a distribution of satellites which has filamentary connection to a main peak as a function of distance. And if you add them all together, you will find the same number, practically the same number as your average over density gives you. So basically what you have a reshuffling of a critical events. They're putting more to the border, but the average number is something the same. And that is a final plot which tells us what is it now, a distribution of the merger events by how many they have had, depending on the height of the peak, so rarity, how rare your halo is. And dependence is not very strong. You does not have to have exactly 2 mergers. It can go maybe up to 6, but the average number of mergers with all these corrections for correlation between things, and even more so, there's even correction for the fact that the halos you're talking about are above the threshold, so there's some layers going on. That's your factor 2. That is 1.9, which you got by simple analytical estimate without anything involved. And that is the end. This is my numbers, 6 for connectivity, 2 for the mergers. It is, again, just to repeat what to remember, it is number of mergers halo experience when it grew by 10 times in mass. And merging satellite are no less than the starting mass of the halo. I'll have to stop here.
Thanks very much, Dmitry. We still have time for some questions, even though there were quite a few already. Glenn, yeah.
Hi, Dmitry. You said this was true for Gaussian fields. Does it depend on the homogeneity and isotropy of the statistics?
Yeah, it does. So it is homogeneous and isotropic field with all peak statistics. You do average over angles uniformly of the distribution of tensors of second derivatives, since there's anisotropy in distribution.
So do you have any sense of how sensitive it would be to?
I hope not. I'm actually the guy who wants to have something which I'm certain about when Dick points me on the grave site of the pictures, right, and there's my grave there. There's a number that I actually have learned something over my life, and not being my chair taken out from below me at the end, right?
Thanks.
Well, you know, Boltzmann has this famous.
Boltzmann didn't end well, right?
So you're going to have 6.1 will be.
Exactly. I want my 6.1.
Prava, you have a question?
Yeah. Dmitry, if I understood.
Sorry, Bruno. Prava first, then I'll take you.
Okay.
Yeah, so how difficult would it be to extend your calculations to an isotropic field?
Half a year of focused work of a good undergraduate student. That's approximately.
Okay. Then there was one more. You had a threshold of 1.3, which came out in your introductory slides.
Yeah.
How significant is that?
Okay, so what I'm lacking in my, what I want to know and I don't have it, I want to understand what physical filament is. We are more talking about geometrical objects, but in reality we want to talk about objects that we see on the sky. Even if they're kind of transient, they're not transient for us, they are on the sky. So in that sense, we need some criteria what part of the filamentary breach is actually observable, corresponds to something which on the sky is. At least density criteria. We don't have even that, like for halos, we have 1.68. We say, okay, that's a halo, right? For filaments, we don't have that. So we do. So it is a first step to point how overdense they should be in initial conditions. In terms of sigma, that is kind of rarity. Peaks are 2.5 sigma objects, somewhere around. Filaments that are important are around 1 sigma objects, as we learned.
Okay.
Then we need a second step. We need to know how it maps nonlinearly when they develop, and to what to criteria to put at the end. And that is not yet done. So you know you.
Yeah, I'm asking because this 1.3, 1.4 comes out in some geometrical objects we are looking at. Yeah. So I'll show you later.
And when we did the percolation with Tarun many years ago in Stephen Columbia, we were just cutting thresholds, and it was our discovery that percolation happens not at 1 sigma, which was a folklore extrapolation from 2D, but actually at a little bit higher level.
Okay.
And that was point of that paper. And this seemingly just supports that. It's probably just simply expression of the same thing.
Yeah. Okay, thanks.
Marco.
Beautiful stuff. Thank you. Dmitry.
Ah, yeah.
If I understood right, in the initial picture, you have all these peaks with the same mass and same volume.
It is something which I want to highlight for people just to remember, that when you see a picture of a smooth field in initial condition, then those peaks do not correspond to the halos that are forming at the same time.
Right.
So,
I mean, can you start from initial condition where you will have like maybe rare peaks which have higher mass in the same volume?
Well, one thing to develop, right, something is adaptive smoothing. So you take your initial field and you adapt it smooth, tracking the fact for all peaks to come up to be the same height. Then it will be your single fixed time picture, right? So actually statistical property of that field, I'm not exactly sure how to deal with, but it's not exactly what you ask, I know. Let's talk a little bit just to try to narrow down it.
Okay, one final question.
Just a clarification, when you're saying mass over here, you mean mass within the smoothing scale, or do you mean at the 1.68?
Whenever you smooth initial conditions, Lagrangian space, right? If you have a picture of spherical collapse in your head, then the mass of the object is basically determined by the smoothing scale. That is what your smoothing scale is.
Yeah, so that's what I guess I just want to. So when you're saying initial mass, you mean the mass within that.
So it is not initial. Okay, let's be corrected. So if you have this picture at a fixed smoothing scale, it means that every peak describes when it forms as a halo, it will have the same mass. Each peak will form the halo at a different time. Yes, okay. So it is different peaks of the same mass, but at different times.
Yes. Okay. Yeah. Thanks.
Okay. Thanks very much. We'll have time for coffee, and we'll meet again at 11:20.
Oh yes.